Hello, everyone, and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Materials Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or with tutoring, then check out the links in the description below. So now let's just get started on our set of questions for today's session. Okay, so question 1 just asks, what is the definition of the concentration gradient? Okay, so the concentration gradient so this is when the concentration of particles is higher in one area and lower in another. Okay, so typically particles will move from higher concentrations to low concentrations. Okay, so they will do that until they are evenly spaced. Okay, so for example, let's say you had a glass of water and you were to add some food coloring to it. Let's pretend we added some green food coloring. Initially, all of the dye or the food coloring would just be in one area of the glass of water. But as time progresses, these food coloring water molecules, they start to become more evenly spaced and will spread all throughout your glass of water till you have just like a green color. Okay, so that's just one simple example of a concentration gradient. So the junior tutor said, the concentration gradient, as the word implies, refers to the unequal concentration of solutes within a specific area. In passive transport, particles will diffuse down the concentration gradient from areas of high concentrations to areas of low concentration in order to achieve equilibrium. Yep, so this solution is correct. Okay, so on to question 2. So it just asks, what is the structure of lidocaine? So lidocaine has the chemical formula C14H22N2O. So now I'll just draw out its structure. We'll start off with a benzene ring. And from there, I'll draw 2 methyl groups. There's a nitrogen functionality connected to a carbonyl. Another nitrogen. And then 2 ethyl groups also connected to that second nitrogen. Okay, so this is the structure of lidocaine. So the junior tutor said, lidocaine is a substance used in the medical field, particularly as a local anesthesia. Its chemical name is 2-diethylamino N,2,6-dimethylphenylacetamide, which shows that this substance is an amide. It also has a benzene ring. The figure below shows the structure. So let's see. Yep, so then they just also gave a link to the structure of lidocaine. Oh, here it is. Okay, so this solution is correct. Okay, so question 3. Given the following chemical bonds, potassium fluoride, fluorine fluorine, bromine fluorine, chlorine fluorine, and calcium fluorine, what is the correct order in terms of increasing covalent character? Okay, so typically we want to look at the difference in electronegativity. So each atom has certain electronegativity value. And when we take the difference between the two of them, which can be shown as delta En, this can tell us how covalent the chemical bond is. So delta electronegativity can just be found by taking the difference between electronegativity of one and the electronegativity of the other. So notice that we're only interested in the absolute value. So if we were to get a negative difference, we would just look at the positive value of that number. Okay, so first let's just find the electronegativity values of all of the different atoms that we're looking for. So we're looking for potassium, fluorine, bromine, chlorine, and calcium. So I'll just search here, electronegativity chart. Okay, so if we look at the value for potassium, it is found here, atomic number 19. It has an electronegativity value of 0.8. Fluorine is at the top right, and its electronegativity value is 4.0. Bromine is below it, 2.8. Fluorine is above bromine, 3.0. And calcium is found on the left side. The electronegativity value is 1.0. Okay, so now that I have all my electronegativity values, I can find the delta En value for all of the different bonds. Okay, so I'll just make a chart showing the bond and then the corresponding delta En value. So first we have potassium and fluorine. Its delta En value is just 4 minus 0.8, which is just 3.2. Next is just a fluorine-fluorine bond. So since they are the same atom, they would just have a delta En value of 0. Next is a bromine-fluorine bond. So it's just 4 minus 2.8. So it's just 1.2. Next, for the chlorine-fluorine bond, it's 4 minus 3, so it's just 1. And then lastly, a calcium-fluorine bond has a difference of 4 minus 1, so it's 3.0. Okay, so when we want to look at how covalent this bond is, when we have a greater delta electronegativity value, the more ionic our bond is. So now we just kind of have to rank from most, no, not ionic, but most covalent character to the least. So the highest delta En value was the potassium-fluorine bond. So next is the calcium-fluorine bond. And then bromine-fluorine. And then chlorine-fluorine. And then the one that has the least covalent character is the fluorine-fluorine. Okay, so let's see what the junior tutor said. Covalent character can be determined by calculating for the absolute difference of electronegativities of the atoms involved in the bond. Mathematically, this would be delta En is equal to the electronegativity value of one minus the electronegativity value of another. Recall that electronegativity is the ability of an atom to attract an electron towards itself in a chemical bond. Generally, the higher the difference, the higher is its ionic character, thus the lowest its covalent character. The electronegativity values of the atoms in the pool of chemical bonds given are shown in Table 1. So here they also just have the electronegativity values of all of their atoms. And then the absolute difference of the electronegativity of the atoms in the chemical bond from the pool are shown in Table 2. Absolute difference of the electronegativity of the atoms in the given chemical bond. So then they also just have all the differences between them. Using the values computed in Table 2, we can now rank them in increasing covalent character. The correct order is potassium, fluorine, calcium, bromine, the chlorine, and then fluorine, fluorine. So this got the two mixed. So when you have a bond that is least covalent, that means it is more ionic. And when you have a bond that is most covalent, that means it is less ionic. Okay, so this solution is correct. Okay, so now we are on to question number 4. Which two functional groups are always found in amino acids? Okay, so an amino acid will always have carbon as the chiral center. And one of the functional groups that is always found on it is a carbonyl group. So draw the alcohol on the right. And the second functional group is an amine. And what makes amino acids unique is that they all contain a unique functional R group. So I'll just denote this as R. But they all have an amine. And they all have a carboxyl. Okay, so let's see what the junior tutor said. Amino acids are building blocks of proteins. Hence, they are considered as one of the most essential biomolecules. A typical structure of an amino acid is shown below. Yep. So you can see how the atom sizes vary depending on how many electrons they have. And R here represents an alkyl group that distinguishes one amino acid from the other. Based on the figure, the two functional groups common to all amino acids are the amine group, NH2, and the carboxyl group, COOH. Yep, so this solution is correct. Okay, so the next question asks, when oxygen and sulfur atoms become monatomic ions, how many electrons does each lose or gain? Which noble gas atom has the same number of electrons as an oxide ion? And which noble gas atom has the same number of electrons as a sulfide ion? Okay, so to answer this question, we would need to know the electron configurations of both oxygen and sulfur, just when they are in their ground state configurations. So for oxygen, let's try to find out its electron configuration. Okay, so oxygen is found here, atomic number 8. And now that we've found it, you'll notice that the periodic table is divided into different sections. So each of that corresponds to a different block number. So the light blue section is the s orbital. This green section is the p orbital. And then this orange section is the d orbital, which is the transition metals. And then the bottom 2 rows is the f orbital. So these are all the lactanides and actinides. So when you write down the electron configuration, you want to start from hydrogen and then move from left to right, top to bottom, until you get to your desired element. So you want to write down the row number first, and then the block number, and then show how many electrons are in each orbital for that atom. So starting at hydrogen, moving on to helium, we write 1s2. And then on to the next row, so 2s2. And then moving to the right, we write 2p, and then count up to the oxygen, 1, 2, 3, 4. 2p4. So when oxygen becomes an ion and it has a 2- charge, what this also means is that it gained 2 electrons. So because it gained 2 electrons, its electron configuration will also change, and we are going to add 2 electrons to the 2p orbital that we ended at. So now our new electron configuration is 1s2, 2s2, and then 2p6. And then if we look at our periodic table, we'll see that it now has the same electron configuration as neon. So I'm just going to write over here, square brackets, Ne. Okay, so that's for oxygen. So let's try to do the same thing for sulfur. So the electron configuration of just a neutral ground state sulfur atom would just be 1s2, 2s2, and then 2p6. And then moving on to the third row, we have 3s2, and then 3p, and we also count 4. Okay, so it's similar to oxygen, except it is just a row under it. So now, again, we'll write what the electron configuration of sulfur would look like if it were to gain 2 electrons. Its new electron configuration would be 1s2, 2s2, 2p6, 3s2, and then 3p6. Again, if we look at our periodic table, it now has the same electron configuration as argon. So I'm just going to put argon in square brackets. Okay, so let's see what the junior tutor said. You can use the periodic table to predict whether an atom will form an anion or a cation, and also predict the charge of the resulting ion. Electrons lost or gained. So oxygen has an electron configuration of 1s2, 2s2, 2p4. Sulfur has an electron configuration of 1s2, 2p6, 2s2, 2p6, 3s2, 3p4. Both oxygen and sulfur are in group 6 with p4 orbitals. As a result, both elements require 2 electrons to obtain a noble gas configuration. Noble gas with the same number of electrons, so they just showed that oxygen with a -2 charge forms an electron configuration similar to neon when it gains 2 electrons, and the sulfur ion forms an electron configuration similar to argon when it gains 2 electrons. Yep, so this solution is correct. Okay, so now let's move on to question number 6. So the molecular formula of acetylsalicylic acid is one of the most commonly used pain relievers. It has a chemical formula of C9H8O4. Calculate the molar mass of aspirin. And part B just asks, a typical aspirin tablet contains 500 milligrams of C9H8O4. What amount or moles of C9H8O4 molecules are there, and what number of molecules are in a 500 milligram tablet? Okay, so this is a multi-step question. And we're going to start by, first I'll just show the chemical compound acetylsalicylic acid. So it has a benzene ring, and it has chemical formula C9H8O4. Okay, so first, part A asks to calculate the molar mass of aspirin. So to do that, we need to find the atomic masses of carbon, hydrogen, and oxygen, and these can just be found on the periodic table. So now, to find it, it would just be 9 times the molar mass of carbon plus 8 times the molar mass of hydrogen plus 4 times the molar mass of oxygen. So now if we look at our periodic table, you'll see that carbon has a molar mass of 12.01 grams per mole. And hydrogen has an atomic mass of 1.01 grams per mole. Lastly, oxygen has an atomic mass of 15.99 grams per mole. Okay, so if we sum up all the values, you end up getting 180.16 grams per mole for the molar mass of aspirin. So now part B. A typical aspirin tablet contains 500 milligrams of aspirin. So we'll write down the mass, which is 500 milligrams. And they're looking for both the number of moles and then the number of molecules of aspirin. Okay, so we know our mass is 500 milligrams, but if we look at the units of our molar mass, it is in grams per mole. So I'm just going to convert the 500 milligrams to grams. So it would be 0.5 grams. Okay, so now let's calculate the number of moles using the equation N equals mass over molar mass. So our mass is 0.5 grams, and molar mass is just what we found in the previous part, which is 180.16 grams per mole. Okay, so this gives us number of moles, which is 2.78 times 10 to the negative 3 moles. Okay, so that's our first answer for part B. I'll just put it in like a box. And then to find the number of molecules, since we already have our value in moles, all we have to do is multiply by Avogadro's number, which is 6.022 times 10 to the 23 molecules per mole. So this cancels out our units in moles, and it gives us the number of molecules in 500 milligrams. So our answer is 1.67 times 10 to the 21 molecules. Okay, so let's see what the junior tutor said. The molar mass of aspirin is 9 times the molar mass of carbon plus 8 times the molar mass of hydrogen plus 4 times the molar mass of oxygen. And they had less decimal places, but still ended up with around 180 grams per mole. The number of molecules of aspirin in a 500 milligram tablet. So they show that it is number of moles divided by Avogadro's number equal mass over molar mass. Okay, so now they just did the 0.5 times 6.02 times 10 to the 23 divided by 180. And they also got 1.67 times, I think they meant 10 to the 21 molecules of aspirin. Still gonna say the solution is correct since they have the same values. But I think it was just a typo. So the solution is still correct. Okay, so the next question, the formula mass of N2O is 44.02 AMU. So that just stands for atomic mass units. What is the mass in grams of 1/2 mole of N2O? Okay, so when we have the formula mass equal to 44.02, this also has the same unit, like the same value as the molar mass, which is in grams per mole. So we can say the molar mass of N2O is 44.02 grams per mole. The question gives us the number of moles, which is 1/2, so just 0.5. And then if we want to find the mass, all we have to do is multiply the number of moles by its molar mass. So pretty straightforward answer. We just need to multiply 44.02 grams per mole by 0.5, which is the same thing as just dividing it by 2. So you'll see that our units for moles will cancel out, and then we're left with 22.01 grams as our answer. So the correct response is C. Okay, so this junior tutor said, the conversion of the mole to mass can be done by multiplying the moles to their molar mass. 1/2 mole means 0.5 moles of N2O, thus 0.5 moles of NTO times 44.02 grams per mole gives 22.01 grams of N2O. Yep, so the solution is correct. Okay, so now let's move on to question number 8. To consider samples of phosphine, water, hydrogen sulfide, and hydrogen fluoride, each with a mass of 119 grams. Rank the compounds from the least to the greatest number of hydrogen atoms contained in the samples. Okay, so we just need to find out basically the mass percentage of hydrogen in all of these different samples. So this is a multi-step question. So first we want to find the molar masses of each of these compounds. Okay, so step 1 is to find the molar masses. So this is just done by looking at your periodic table and finding out the atomic masses of each of the atoms involved in the compound, and then just multiplying them if we need to by how many atoms there are of each in the compound. So for example, the molar mass of fluorine would just be equal to the molar mass of phosphorus plus 3 times the molar mass of hydrogen. So the molar mass of phosphorus is 30.974 grams per mole. And the molar mass of hydrogen is 1.01 grams per mole. So the total molar mass of phosphine ends up being 34.0 grams per mole. Okay, so next let's do the molar mass of water. This is just 2 times the molar mass of hydrogen plus the molar mass of oxygen. So again, the molar mass of hydrogen is 1.01 and the molar mass of oxygen is 15.99. So its molar mass around 18.01 grams per mole. So next we have hydrogen sulfide. So its molar mass is just 2 times the molar mass of hydrogen, which is 1.01, plus the molar mass of sulfur, which is 32.06. Okay, so this gives us a molar mass of 34.08 grams per mole. And then lastly, we have hydrogen fluoride. So its molar mass is just 1.01 plus 18.99 is just around like 20 grams per mole. Okay, so now that we have all of the molar masses, the second step is to find all the number of moles when each of their masses is 119 grams. Okay, so starting with phosphine, to find number of moles, it's just going to be mass over molar mass. So we know that our mass is 119 grams, and our molar mass of phosphine is 34.0 from the previous step. So this gives us the number of moles, which is 3.5. Okay, so now let's do the same thing for water. It is 119 grams divided by 18.01 grams per mole, which is equal to 6.6 moles for water. Number of moles of hydrogen sulfide is the 119 grams divided by 34.08. Okay, so its number of moles is 3.5. And then lastly, for an HF, it is 119 grams divided by 20. Okay, so this is 5.95 moles. Okay, so now that we have all of the number of moles, we want to find out the greatest number of hydrogen atoms contained in the sample. So for part 3, maybe I'll do this on another page just so that we have more room. Step 3 is just to multiply by Avogadro's number. And also how many atoms of hydrogen there are in each compounds. Okay, so starting with phosphine, we found its number of moles to be 3.5 from the previous step. We need to multiply by Avogadro's number, which is 6.022 times 10 to the 23 molecules per mole. And as for the number of hydrogen atoms, there are 3 H atoms in one molecule. So these units will cancel out, our moles will cancel out. And for phosphine, we get 6.33 times 10 to the 24 hydrogen atoms. Okay, so next let's look at the water. Its number of moles was 6.6. Multiply it by 6.022 times 10 to the 23. And in water, there are 2 hydrogen atoms. So then this gives us 7.95 times 10 to the 24. Next, we have hydrogen sulfide. So its number of moles was also 3.5. And it had 2 hydrogen atoms in one molecule of hydrogen sulfide. So then this gives us 4.22 times 10 to the 24. And then finally, let's look at hydrogen fluoride. So its number of moles was, I think, 5.95. Yeah. Okay, so we're multiplying by Avogadro's number, molecules per mole. And in hydrogen fluoride, there's only one hydrogen in one molecule. Okay, so this gives us number of atoms to be 3.58 times 10 to the 24. Okay, so lastly, we need to rank from least to greatest number of hydrogen atoms. Okay, so now let's just look at all of our values. The lowest number is hydrogen fluoride. And then next is hydrogen sulfide. And then phosphine. And then water has the greatest number of hydrogen atoms in the sample. Okay, so now let's just see what the junior tutor said. Get the number of hydrogen atoms in each compound. We use the Avogadro's number and the subscript of each atom. Also use the molar masses of each compound using the atomic masses of each constituent element. Okay, so first they just wrote down all of the atomic masses of phosphorus, 30.97, hydrogen 1, oxygen 15.99, sulfur 32.06, and fluorine 18.99. We express the number of atoms in terms of Avogadro's number Na. So notice that they don't actually multiply by the 6.022 times 10 to the 23. So this might make it easier just so that we have, so just so that we're working with just easier numbers. Since all of them are multiplied by Avogadro's number, we just need to see the largest after you multiply by however many hydrogen atoms. So here you can just see they fit it all in one line. So starting with 119 grams of phosphine, they divided by its molar mass, which was the 30.97 plus 3. And then they showed how you would convert to molecules. And then they showed how the molecules will cancel out if you multiplied by atoms. Okay, so they got 10.5. So if we were to multiply this 10.508 by the 6.02 times 10 to the 23, then you would get the 6.33 times 10 to the 24. But this is still correct. Let's see what they did for water. The same thing. 13.22. Hydrogen sulfide, 119 times 1 over 32 plus 2. And then they multiplied this by 3. And I think it should have been 2. But it could have just been a typo. Let me just double check. This would be equal to. Yeah, so they meant to write 2 hydrogen atoms, but they still got the 6.987. And then lastly, hydrogen fluoride, 119 divided by 18.998 times 1. Yep, so this solution is correct. I'll just take note of typo for hydrogen sulfide. Okay, but this solution was still correct. So that's all for this session. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. If you'd like to submit a question of your own, then check out the links in the description. And also, if you liked today's video, you can just give it a like and a comment, and you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon. Bye.